fluorine coupling of 85 Hertz. And for this one, the coupling with boron is 0, so we only have a doublet. And in fact, we have two doublets. We have 80% of the doublet for the molecule with 11 boron, and 20% of another doublet with for the molecules bearing 10 boron. And we have a small shift here between the boron 10 and boron 11. And so we have two superimposed doublets. So, heteronuclei can sometimes lead to funny patterns, and they can be used for correlation experiments. So again, in this experiment, we can make many experiments. For phosphorus, for example, it's very easy to make proton-phosphorus correlations. I won't show them to you today, but on the same molecules that are shown on the previous slide, here we used standard proton nosy, and we have seen that we had correlations between the methyl here and this proton, the methyl here and this proton, for example. And we used dipolar correlation between proton and fluorine, and we could attest that the fluorine here was on the same side than this proton here. We had a dipolar coupling, a through-space coupling between this proton and this fluorine. Okay, so we can make many different experiments with heteronuclei. Sorry. So if you have some, just ask, and we can make many things. Okay, just a small focus on some special two-dimensional experiments which can be asked for in routine. They are available in the sample changers list. This is band selective two-dimensional experiments. So the example is always the same. It's a quinine sample, so it's not really crowded, but sometimes, especially if I often use these experiments for elicens, for example, when you have a very crowded region in your carbon spectrum, sometimes you need to improve the resolution of the two-dimensional experiment. A two-dimensional experiment is composed of several parts. The preparation part, then the signal is, we let the signal evolve during an evolution period, then a mixing scheme, and detection. The resolution of the two-dimensional experiments in the F1 dimension, the vertical dimension, depends on the number of different spectrum we make, and this parameter is called the TD in F1 dimensions. And the resolution is proportional to the TD, but the experiment duration is also related to this parameter. So increasing the resolution by only increasing the TD can be very time-consuming. So it could be interesting to reduce the spectral window in the F1 dimension. But if we just do this, just choose just reduce the spectral window and nothing more. For example, here, if I only detect signals, between 40 and 55 ppm, you can see that I have much more resolution here. My peaks are really precise in the carbon dimension, but I get some folded peaks for the peaks that would be outside from my window. For example, these three ones, 1, 2, 3, will be there, 1, 2, 3. So it's not their real chemical shifts because they are fold over the spectrum. To avoid this and to get a good carbon resolution on a precise region of the spectrum, we can use a band selective experiment. It means that we will only excite the signals in a precise region. Okay, so this is a large window, but with a band selective excitation. So we only see these peaks. And if we use the reduced window, we have our peaks with a better carbon resolution and no folding. Okay, so these band selective experiments are available on the sample changers. So if you need them, we have them with 2 bandwidth. Usually we have normal HSQC and band selective HSQC with a 50 ppm window or a 30 ppm window, and you have to set the offset to know if you want to look in, for example, in this region or in the aromatic region. You have to set the offset of the experiment. So it's not difficult. If you need help to set it up on the sample changer, just ask. But it can be very useful for crowded region. And it's quick. Okay, last thing that could be used for observing interaction or correlations, but quicker than with a standard 2-dimensional experiment, is to use selective 1D experiments. So because recording a 2-dimensional experiment can be very long, sometimes several hours. And in some cases, we can get the information with selective 1-dimensional experiments. For example, here, so this is a toxi. So we want to look at the scalar couplings along the spin system. So here, for example, so I just show you on the next slide. This is the standard proton spectrum. And here we started from this peak. It was selectively excited, this one. And with the selective toxi, we get the signals or only this spin systems. And on the other spectrum, we started from here and we get the signals from the other spin system. So this can be very quick. It's not routine experiments because several parameters have to be set and it's not straightforward. But if you need to perform this type of experiment, it's very easy. And it can be done quickly. For example, the 500 megahertz in CRM-PO, we can just set this up in a few minutes. Okay, just a few slides on programming tips to save spectrometer time. Please remind that your signal to noise ratio is only proportional to the square root of the number of scans. So increasing the number of scans is not the only solution. If you have some compound, put it in your sample. So because increasing number of scans is very time consuming. Don't increase the number of scans for 2D experiments if your proton spectrum is okay. So especially for heteronuclear experiments, or I often see some very, very long experiments, and often it's not really useful. In homonuclear correlation 2D experiments, you could even get a worse result with increasing number of scans, because it will increase the duration of the experiments, and it will increase what we call the T1 noise, which is related to the spectrometer instabilities during the experiments. And so for homonuclear 2D experiments, such like COSY, for example, if you increase the number of scans, you will get a worse spectrum than if you let the standard, that is the standard parameters. When you have to program with, when you have to make a complete analysis, my advice is to start with during at night. Here it's a sun, but it should be a night series. Start with the carbon-13 spectrum, because it's quite long and it's not very sensitive to the temperature, and the settings of the spectrometer will continue to improve during the carbon spectrum. Then proton, then two-dimensional experiments, the one you need according to your sample. And if you have a long two-dimensional experiment series, always end with another proton spectrum, which would be useful to check if your compound is still okay after the other experiments. It's really important to have a proton spectrum that will be recorded at the same time than the two-dimensional experiments. So even if you got one during the day, if you ask for a complete analysis, ask for the proton spectrum again. It's very important. And don't hesitate to ask for another one at the end of the two-dimensional experiments. But please don't use JMOD or depth anymore if you ask for the HSQC. HSQC will be very short experiments, usually only 10 or 15 minutes, and JMOD or depth are insensitive techniques because they are direct carbon-13 observation, and so they are longer. So if you want to save spectrometer time, just ask for the direct carbon detection and then two-dimensional experiments. Another small tips about Anova software. So on the intranet, you can find a webinar. Since I have no scheduled training session anymore, but so you can find tips and webinars for the Anova use. When you work well, you can get some fully assigned two-dimensional spectrum, and it's really easy to work on this when you have the molecule and with the number, and so you can see on your two-dimensional spectra all the correlations and easily check them and make the assignment. A small thing in Anova, if you want to make the name of the observed nucleus appear on the axis here instead of F1, F2, you just have to go in the properties, go into the scales, so horizontal and vertical scales, and modify here the label. If you have several codes, and if you want to make appear the observed nucleus, it's very easy, and if you set it as default parameters, every time you will open a new spectrum, you will have the nucleus, and it can be very useful, especially if you work with heteronuclei like fluorine or phosphorus. Each time you will open a spectrum, you will know which nucleus is being observed.
So just a quick question. So I can't read it. It's a little bit too small. So it's $3N or what?
No, it's $1N, but you can see it when you go on the properties of the Anova. You just select, and if you put your mouse in this area, it will appear.
Okay.
And on your own computer, you will be able to read it.
Second quick question. You said on the internet we can find webinars. This means...
Yeah, I will just show it just in a few seconds.
Yeah.
Okay, so just a small reminder about NMR spectrometers available. So we have every spectrometer, every routine spectrometer can be used for any team. So you can use the spectrometer you want, except 411A building, which is only available for on Friday plus weekend. The 300 megahertz 11A building is still under test. We had many problems with the manufacturer. It's getting better. I hope in a few days we can put it back in routine again. Okay, don't hesitate to ask for a level 2 training if you need to use 500 megahertz for non-routine experiments, such like variable temperature or kinetics or other things. And every user can ask to have an access to PRISM spectrometers in Villejean. One of the 500 megahertz is fitted with a cryoprobe. A cryoprobe works at room temperature. Your sample won't be frozen, but since the electronic parts are cooled with a very low temperature helium gas, it decreases the noise, and so it increases very much the signal to noise ratio of your spectrum. So if you have a very small quantity of compound, you can use a cryoprobe. It's very interesting. Usually the duration of a carbon spectra can be reduced of a factor 4 or maybe 8. So if you need to use this cryoprobe, just ask. And another spectrometer is available with different probes. Especially we have one, I forgot it. We have one with a triple resonance probe which can perform phosphorus decoupling with the proton decoupling. So for example, you could get carbon spectra with both proton and phosphorus decoupling if you have complicated carbon spectrum because of coupling to phosphorus. We can work on this spectrometer. So if you need to ask for a special experiment, you can go on the intranet. So I will switch to the real intranet. So this is a real web page. In this section, so the NMR Support section, you can open tickets. So this is a help desk, and you can open tickets if you encounter problems about, for example, the cloud or spectrometer, if there are some failure, outage, some problems with the hardware. You can ask for training. You can ask for scientific advice, or if you need some specific experiments in Villejean or here. And if you have some question about the planning or anything. Just go back. Here you will find some documents. And for example, in the training about the data processing with Anova will be here. Mm-hmm. It's just video recording of a presentation we made last June, so it's not really good video, sorry, but it can be found here if you need it. Okay, here you can see the rules of sample changer. You can see the calendars for priorities. And for example, you can see the sample changer, which is running. So you can check, is there many samples waiting or not? Is my sample finished or not?
And just a quick comment for the for the password, it's not the same password for the 400, huh? At the